Hello students, myself Venkat, chemistry faculty from Sri Chaitanya, and in this session as a part of Sankalp 2.0 we are going to discuss another important chapter called electrochemistry. So let us discuss this in the most useful way so that you can answer the questions that are given from this chapter. Generally 2 to 3 questions are given. Most of the times 3, rarely it is 2. Those 2 or 3 questions are given from this chapter. Let us divide this chapter into 3 parts and discuss the main areas of each of the subtopic. So electrochemistry, it has 3 parts like conductance, electrolysis and galvanic cells. So we shall discuss these 3 subtopics individually along with the important model questions that can be given based on each of them. Let us start with electrolytic conductance or conductance of electrolytic solutions. Actually, there are two types of conductors, metallic conductors and electrolytic conductors. Metallic or electronic conductors are the substances which carry electricity through electrons as the charge carriers, and electrolytic conductance is through migration of ions between electrodes in a conductivity cell, just like this. In conductivity cell or in electrolytic conductance, we have some important terms. Let us see them, each of them once. See, if this is the conductivity cell, these are the electrode plates. They have some area A, area of each of the electrode plate is A, and if L is the distance between these two electrodes, then resistance is offered by this. There is certain resistance offered by the electrolyte, just like an electronic conductor, but this electrolytic conductor's resistance, it decreases with increase in temperature, or conductance will increase with increase in temperature. It is a differentiating point for electronic conductors and electrolytic conductors. So every electrolyte has certain resistance, and this resistance R is proportional to this L by A, that is distance between electrodes by area of the electrode plates. R is equal to a constant rho into L by A, where resistance R has units of ohm, and this term rho is called as resistivity. And resistivity is equal to R into A by L. That means the units of resistivity will be ohm meter square by meter, that is ohm meter. These units are important related to each of the term that we will discuss now. The units are very important. Resistance has units of ohm, ohm, and resistivity has units of ohm meter or ohm centimeter. Then how do we define this resistivity? Resistivity is resistance of an electrolyte that is taken in a cell with unit distance of separation between electrodes and unit area of electrode plates. Unit distance between electrode plates and unit area of electrode plates. If that is the case, that means L and A, if they are 1 and 1, resistivity will be equal to resistance of that solution. Okay, so this is resistance and resistivity, and the next term is conductance G, which is reciprocal of resistance 1 by R. This conductance has the units reciprocal to resistance, so it has the units of ohm inverse or ohm inverse, or it is also expressed in Siemens, that is S, capital S is the symbol, small s for second and capital S is used for this Siemens. The relation between resistivity and this conductance, for example, G is equal to 1 by R, that means 1 by rho of from this 1 by R, 1 by rho of reciprocal of L by A by L. That means it is 1 by rho of A by L, where this 1 by rho is resistivity, reciprocal of resistivity is called as conductivity. Kappa is the Greek alphabet, kappa is its symbol, kappa into A by L, or kappa is equal to G into L by A again. This is formula for conductivity. Conductance has units of Siemens. Then conductivity has units of Siemens meter by meter square. Siemens meter inverse or Siemens centimeter inverse. These are the units of this term conductivity. Resistance ohm, resistivity ohm meter, conductance ohm inverse, conductivity Siemens meter inverse or Siemens centimeter inverse. So these are the four basic terms related to it, and here also we have another important term. If in a conductivity cell, if L is the distance between electrodes and A is the area of electrode plates, we define the term called cell constant for it, and that cell constant G star is nothing but L by A. This particular ratio is constant for a given electrolytic cell or conductivity cell, and it is called as cell constant. And what are its units? Meter by meter is meter square, that will be meter inverse or centimeter inverse. So related to this, these are the important terms. Units are also important. Let me define conductivity finally. Conductivity is the conductance of an electrolyte taken in a cell of unit distance between electrode plates and unit area of electrode plates. Or in the other way, you can define it as the conductance of, total conductance of unit volume of electrolyte. If L is 1 centimeter and area is like this, if I take two electrode plates, if length is 1 centimeter and area is also 1 centimeter square, then the volume enclosed between this area, this total volume, this will be equal to 1 centimeter cube. That means it is unit volume. If L is 1, A is 1, then total volume of it will be, total volume enclosed between those electrodes will be 1 centimeter cube. So we can define conductivity as conductance of unit volume of electrolyte. This is the best definition that is useful in explaining the effect of dilution on conductance and conductivities. Similar to this four terms, we also have another important term related to electrolytic conductance, that is molar conductance. Actually, we have molar and equivalent conductances, but in NCERT, they didn't mention anything related to equivalent conductivity. So we can proceed with molar conductance or molar conductivity. Both are used with the same meaning, molar conductivity and molar conductance, but it is conductivity is more important term. Actually, conductivity kappa is also called as specific conductance. Conductivity is specific conductance. Resistivity is specific resistance. So molar conductivity, lambda is the other term. Either conductance or conductivity, they do not have any concentration term, or they do not relate the concentration of electrolyte. So the best term related to conductance for a given solution of a particular concentration is molar conductivity. This molar conductivity is the total conductance of 1 mole of electrolyte present in a given volume. I mean, 1 mole of electrolyte, 1 mole of electrolyte is the criteria. When 1 mole of electrolyte is present in a given volume, whatever is the volume V, then the total conductance is called as molar conductivity. So lambda m, actually K is actually, assume that 1 mole of electrolyte is in V volume, 1 mole electrolyte in V volume, then it is molar conductance. The total conductance of that total solution will be molar conductance. If K is the conductance of unit volume, then total conductance of V volume will be molar conductivity, and that will be equal to, if K is for unit volume, K is the conductance of unit volume, the total conductance of volume V will be K into V. This is an expression for molar conductivity in terms of K and V, but on modification of it into the concentration term, we will get lambda m is equal to K into 1000 by molarity in the units of Siemens centimeter square mole inverse when K is given in Siemens centimeter inverse, and molarity it has the same units, moles per decimeter cube. Moles per decimeter cube. 1000 is to modify the unit. Actually, this can be taken as 1000 centimeter cube per decimeter cube. So you can skip that, but remember that when K is given in Siemens centimeter inverse and molarity, it has conventional units of moles per decimeter cube, you will get lambda m in Siemens centimeter square mole inverse when you use this formula K into 1000 by m. But if it is required in Siemens meter square mole inverse unit and K is given in Siemens meter inverse, then if we use this relation, K by 1000 into molarity will give you that accurately. So use these two formulae according to the given value of K, the mean units of K as well as the units of lambda m required. So let's see some questions related to each of these. First one is related to those conductance, resistance, conductivity, molar conductivity, all these relations. Resistance of a conductivity cell filled with 0.1 molar KCl solution is 100 ohm. So there are two solutions which are taken in the same conductivity cell. That means L by A is same for them. I'll take first solution, which is 0.1 molar solution of KCl. For this, resistance given is 100 ohm, and for the same solution, the conductivity of the same 0.1 molar KCl solution is 1.29 Siemens per meter. That means Siemens meter inverse. In the same conductivity cell, now another solution is taken whose concentration is 0.02 molar, again KCl. It is KCl, but with different concentrations, there will be different resistance and conductance. For this, resistance is given as 520 ohm. And now the question is to find its conductivity K2 and molar conductivity lambda m2. Let's calculate that. For a given solution, K is equal to 1 by R into L by A, that is GL by A. But when you take it for two solutions in the same conductivity cell, L by A is constant, so K is inversely proportional to R. So you can take K1 by K2 is equal to R2 by R1. That means K2 is equal to K1 R1 by R2, which is K1 is 1.29 into its resistance 100 by resistance of second solution 520 directly 520. So this will be in Siemens meter inverse only, and it is 129 by 520, which is something around 0.248. This is resistivity, this is conductivity of this solution in Siemens meter inverse unit. For the same solution, let us calculate lambda m. Lambda m is equal to K into, see, look at this. This is given in Siemens meter inverse. So I will take the formula as K by 1000 into molarity. So that is 0.248 by 1000 into molarity that is 0.02, which is 0.248 by 20 Siemens meter square mole inverse, which is equal to 0.0124 Siemens meter square mole inverse. Like this. They may not give you both at a time in a question. They either ask you to find lambda m, or they'll stop the problem with K2 of the solution. So this is the approach to solve a question related to conductance. Let us go to the next part. It is connected with the same electrolytic conductance, which is the concept of dilution on electrolytic conductance. When an electrolyte is, or electrolytic solution is diluted, what happens is the total volume increases, ionic interaction between the ions will decrease in case of strong electrolyte, and if it is a weak electrolyte, degree of dissociation will increase. As a result, either because of decrease in ionic interactions or because of increase in number of ions, the total conductance will increase. If total conductance increases, if it is for 1 mole of electrolyte, if the total conductance increases, molar conductance or molar conductivity will also increase. So molar conductivity will increase with dilution, but conductivity will decrease. It's because as the total volume is increased, assume that it is initially this volume in which the 1 mole of electrolyte is present. Now it is diluted to, assume it is, if it is 1 liter and now it is diluted to 4 liters, the number of all the ions are now distributed in the total volume, but conductivity is defined only per unit volume of electrolyte. That means conductivity is only conductance of this volume. The number of ions in this volume is decreased due to dilution as the volume increased. So the total conductance of unit volume decreases, or the conductivity value decreases. Conductivity decreases due to dilution because of decrease in number of ions per unit volume. So that is the case of dilution. So as a result, finally with dilution, or with, if concentration decreases with dilution, as concentration decreases, K value decreases. That means C is directly proportional to K and lambda m increases. Yes, it increases with dilution. How far it will increase? It will increase until it reaches a maximum value where ionic interactions become 0, or degree of dissociation in case of a weak electrolyte becomes 1. That is the upper limit of this lambda m value, which is called as lambda naught m, which is limiting molar conductivity or molar conductivity at infinite dilution. So this is the highest value possible for a given solution, and that is limiting molar conductivity. Now this limiting molar conductivity and molar conductivity of a particular electrolyte for a strong, especially strong electrolyte, not for weak electrolyte, is only for strong electrolyte. These two are related as lambda naught m is equal to lambda m minus A of root C, which is called Debye-Huckel-Ansager equation, that can be used to get the value of lambda naught m if you have different lambda m and C values. When you are provided with two lambda m and C values, you can substitute them in this expression. You can cancel A to get lambda naught m, where A is a constant which depend on type of electrolyte. Like if 1,1 type of electrolyte like NaCl are taken, all those electrolytes of 1,1 type will have same A value. Similarly, 2,2 type will have a particular A value. So let us not go into the details of this concept. Let us mainly focus on the numerical areas. So lambda naught m is equal to lambda m minus A into root C is the other formula that is important. Now, so at what happens at infinite dilution? As I said, the ionic interactions are vanished. As ionic interactions become 0 at infinite dilution, every ion has its own individual migration effect. That means conductance offered by every ion is independent of the presence of other ion or nature of other ion present along with it. For example, Cl minus is taken. when it is along with K plus or with Na plus, its ionic conductance will be constant when the concentration is limiting value or when it reaches to infinite dilution case. So that means ionic conductance at infinite dilution has a fixed value for a particular ion, and that ionic conductance actually is inversely proportional to size of the hydrated ion. So now the concept of Kohlrausch law is at infinite dilution, because every ion has certain individual contribution to the total molar conductance. Now Kohlrausch law is stated as, according to Kohlrausch law, the total molar conductance of an electrolyte at infinite dilution is equal to sum of the contributions of ionic conductances of all the ions present in it. That means if I take NaCl, for NaCl, lambda naught m at infinite dilution is equal to sum of the ionic conductances of both the ions present in it. That means lambda naught m of NaCl is equal to lambda naught m of Na plus lambda naught m of Cl minus. For ion total compound molar conductivity, we use uppercase lambda, and for ionic conductance we use small case lambda in Greek alphabets. So lambda naught m is equal to lambda naught of Na plus Cl minus. Similarly, for any given electrolyte, you can write it as a general formula, nu plus into lambda naught plus nu minus into lambda naught minus. So what it is, where nu plus and nu minus are number of cations and anions that are produced by dissociation of electrolyte. Like NaCl, when it dissociates, it gives one cation, one anion. So those nu plus and nu minus are respectively the number of ions produced by each of the electrolyte, and lambda naught plus lambda naught minus are the respective ionic conductances. If it is equivalent conductivity, there won't be any such coefficient for a simple electrolyte which has only one type of cations and one type of anions. So if it is required, you can apply that. Lambda naught EQ is equal to simply ionic equivalent conductivity of cation plus ionic equivalent conductivity of anion. For molar conductivity, we have to take this number of ions, because it depends on the concept which we use to derive that expression. Now let us take it for certain examples. Take for example K2SO4. For K2SO4, lambda naught m becomes, there are two K plus ions, so 2 into lambda naught of K plus lambda naught of SO4 2 minus. Similarly, if it is Al2 SO4 thrice, you have to write it as 2 into lambda naught of Al3 plus 3 into lambda naught of SO4 2 minus. That means the coefficients, number of ions multiplied by ionic conductance, number of ions multiplied by ionic conductance. So this way you can give the mathematical expression for Kohlrausch law. According to Kohlrausch law, at infinite dilution, the total conductance of a particular total molar conductance of a particular electrolyte is equal to sum of the ionic conductances of all ions present in it. Now we have some important applications related to it. Actually, this is useful. Lambda naught, this Kohlrausch law is most useful in finding out the lambda naught m values for weak electrolytes, which is not possible experimentally, because at infinite dilution the conductivity value will be very low, so we cannot measure it properly, so we cannot get lambda naught m from that conductance part. We cannot even get it from the graph between lambda m and root c, because for a weak electrolyte, lambda m and root c graph is not a straight line to know where it touches the y-axis. You cannot extrapolate this graph to get lambda naught m for weak electrolyte, but for a strong electrolyte, it is simply a straight line which can be extrapolated or extended to get lambda naught m. This is for strong electrolyte, this is for weak electrolyte. So for weak electrolyte, the best way to find lambda naught m is this Kohlrausch law. Let us see how to find that. Let me take an example. Assume this lambda naught m of a strong electrolyte HCl is some x. I'll take random numbers instead of exact values. Lambda naught m of HCl is x. Lambda naught m of CH3COO Na is y. Lambda naught m of NaCl is z. See, I have taken three strong electrolytes. These three strong electrolytes are taken, which can be used to find lambda naught m of a weak electrolyte, that is acetic acid. With the help of strong electrolyte which contains these ions, we can find lambda naught m of this acetic acid. Actually, lambda naught m of acetic acid can be written as lambda naught m of acetate plus lambda naught m of H plus. This is obtained from these values also. Actually, lambda naught m of H plus is lambda naught m of H plus lambda naught m of Cl minus. This is lambda naught m of acetate plus lambda naught m of Na plus from Kohlrausch itself. This is lambda naught m of Na plus lambda naught m of Cl minus. See, if you observe these three values, you can get this by using these three values. Say these are three equations, 1, 2, 3. One has H plus, which is required here. 2 has acetate ion, which is also required. So I will take 1 plus 2. And we also have two unwanted ions, Cl minus and Na plus. To remove them in this expression, like if you add these two, you have Cl minus and Na plus. To remove these two ions, we subtract the value of lambda naught m of NaCl from these two. That means 1 plus 2 minus 3. That is lambda naught m of HCl plus lambda naught m of CH3COONA plus lambda naught m of Na minus lambda naught m of NaCl will give us the required data. Minus lambda naught m of NaCl. This is equal to this lambda naught m of CH3COOH. Observe that. You will get this expression when you add these two and subtract this from them. So finally, lambda naught m of acetic acid will be equal to this x plus y minus z. This is how to find lambda naught m of a weak electrolyte when the corresponding strong electrolyte values are given. Let me take another example. If I want to find lambda naught m of H2CO3, I must be given with compounds, strong electrolyte values which have H plus and carbonate, and the other third one to remove the unwanted ions. See, lambda naught m of, assume that it is HCl given as some A, lambda naught m of K2CO3 is B, then lambda naught m of KCl is C. See, how do we get this? Two H plus ions are required. Two H plus ions are required in H2CO3. So I will take 2 into lambda naught m of HCl plus 1 carbonate. So I will take directly lambda naught m of K2CO3 minus KCl. But actually I took 2 into lambda naught m of HCl. That means there are 2 chloride ions and 2 K plus ions which should be removed. So I should subtract 2 into lambda naught m of KCl to get the lambda naught m of H2CO3. So similarly, if you write the expressions for these, you will get the same result. That means it is equal to 2A plus B minus 2C. So this is one of the applications of Kohlrausch law to find lambda naught m of a weak electrolyte with that of strong electrolytes. Let us see some more questions. So this is a theory question related to electrolytic conductance, especially for conductance, the effect of conductance on ionic size. Ionic conductance lambda naught of ion is inversely proportional to size of hydrated ion. Size of hydrated ion. Actually, size of hydrated ion in turn is inversely proportional to size of gaseous ion, because a smaller ion gets more hydrated. A smaller ion gets more hydrated. So size of hydrated ion is inversely proportional to size of gaseous ion, and this is lambda naught m is finally directly proportional to size of gaseous ion. In case of aqueous electrolytes, see, look at this. The question is the correct order of molar conductance at infinite dilution. At infinite dilution means for a solution itself. Within that solution, lambda naught of each ion. Actually, if you observe all these compounds given, they have a common anion, chloride. So the resultant, the deciding factor is cation. The size of cation will decide. Actually, size of cations follow this order. K plus gas is greater than Na plus gas is greater than Cl minus gas. Li plus gas. This is the gaseous ion size. And if it is hydrated ion size taken, K plus aqueous is smaller than Na plus aqueous, which is smaller than Li plus aqueous. That means the conductance will be in the opposite order. Size of it is inversely proportional to size of hydrated ion. So lambda naught of K plus aqueous is greater than lambda naught of Na plus aqueous, which is greater than lambda naught of Li plus aqueous. So this is the order of ionic conductances. That means at infinite dilution, the molar conductances of these compounds will follow the order KCl greater than NaCl greater than LiCl. So this is the order. This is a theory question related to that. Next, we see another example, another application of Kohlrausch law. According to Kohlrausch law, for a weak electrolyte, we can derive an expression for degree of dissociation of a weak electrolyte. That is, number of moles dissociated out of 1 mole at a given concentration alpha. We can prove that degree of dissociation of a weak electrolyte is equal to lambda m for the given concentration C by lambda naught m. Molar conductance for the given concentration is directly proportional to number of moles of ions present at that concentration, which is proportional to the quantity that is dissociated at that time by total conductance at infinite dilution, that is by total number of ions, number of moles dissociated by total number of moles taken, because number of moles dissociated is directly proportional to lambda m, and lambda naught m is directly proportional to total number of moles taken initially, because that will be present finally at infinite dilution. So alpha is proportional to lambda m by lambda naught m. Then similarly, for a weak electrolyte, say Ha, H plus plus A minus is the dissociation equilibrium. Ka is equal to, if C is the initial concentration and alpha is degree of dissociation, C alpha will be the quantity that reacts. C alpha is H plus concentration. C alpha is also A minus concentration. For this equilibrium, you can get Ka, expression for Ka as C alpha square by 1 minus alpha. For a weak acid, Ka equal to C alpha square by 1 minus alpha. For a weak base, Kb is equal to C alpha square by 1 minus alpha, and that means it is equal to C into lambda m by lambda naught m square by 1 minus lambda m by lambda naught m. So this is the expression to find dissociation constant for a weak electrolyte when lambda m and lambda naught m values are given. Now apply this to solve this problem. So what is the data given? Lambda naught m of H plus and lambda naught m of formate ion are given. So lambda naught m of methanoic acid, that is formic acid. HCOH is equal to lambda naught m of H plus lambda naught m of HCOO minus, which is according to Kohlrausch law, so that is from 349.6 plus 54.6 Siemens centimeter square mole inverse, that is actually equal to 404.2 Siemens centimeter square mole inverse. This is lambda naught m, which we have, lambda naught m compound. Molar conductivity for the given concentration, for 0.025 molar concentration, it is already given as 46.1. That means alpha is equal to lambda m by lambda naught m. What is asked in the question? Degree of dissociation as well as dissociation constant. So let us first find alpha, lambda m by lambda naught m, 46.1 by 404.2, which is around 0.114. This is alpha value. Then how do we find Ka of the same? With this formula, after getting alpha, you can substitute the data in this formula, C alpha square by 1 minus alpha. C is 0.025 into alpha, you can approximate it to 0.11 or 114 exactly, square by 1 minus 0.114. You cannot approximate this. You cannot write 1 minus alpha as 1 when alpha value is greater than or equal to 0.05. You can approximate it only when it is very low. But when it is in the range of 0.11, it's not negligible compared to 1. So you retain it and solve it to get the final dissociation constant of that. So simplify it to get the final answer. Okay. So this is an important model related to Kohlrausch law. Next, let us move on to the very important part, electrolysis. Electrolysis has two areas, qualitative aspect, where we discuss the nature of products obtained as a result of electrolysis, and quantitative aspect, quantitative electrolysis, that is the relation between charge passed and the mass of substance deposited. So this quantitative aspect is discussed with the help of Faraday's laws. The qualitative aspect, the nature of products deposited at electrode depends on the nature of electrolyte, whether it is aqueous or molten, and it also depends on whether the electrodes taken are active or inert, or it also depends on concentration. I'll explain briefly the concept of it through a question, but let me proceed with Faraday's laws. Faraday's first law, according to Faraday's first law, the mass of substance deposited at an electrode is directly proportional to charge passed. M is proportional to Q, M is equal to Z into Q, where Z is called as electrochemical equivalent, and that is equal to equivalent weight by 96,500 into Q. Electrochemical equivalent is related to equivalent weight of that substance deposited, as Z is equal to E by 96,500 into Q, or you can write M is equal to E by 96,500 into I into T, where I is current in amperes, T is time in seconds, E value is equivalent weight, then you will get mass. If you substitute the gram equivalent weight here, you will get mass in grams, mass of substance. So this is the mathematical relation for Faraday's first law. And from this, you can also get another relation. M by E is equal to Q by 96,500. So what is the significance of this formula? Mass by equivalent mass of substance. Mass of substance by equivalent mass is nothing but number of equivalents. Number of equivalents. Charge in coulombs by 96,500 is charge in Faradays. That means, according to the same law, you can also say number of equivalents of substance deposited is equal to number of Faradays of charge that is used. So equivalents, number of equivalents is equal to charge in Faradays. This formula is or this relation is most useful in solving the questions like that given in NEET 2025. So let me explain an example with that. And this is the relation for Faraday's first law and the mathematical form for second law. According to Faraday's second law, when same amount of charge is passed through different electrolytes, the ratio of masses of substances deposited is in the ratio of their equivalent masses. Same amount of same charges passed through different electrolytes. Look at this. Same charges passed through different electrolytes. The ratio of masses of substance deposited is equal to the ratio of equivalent masses. That means M is proportional to E when Q is constant. From the same, you will get that relation. That means M1 is to M2 is to M3. That is all equal to E1 is to E2 is to E3. This is the mathematical form for second law, Faraday's second law. Let us solve some questions related to each of them. First one is related to qualitative electrolysis. Look at the question. During the electrolysis, it's a different model. During the electrolysis of an aqueous salt solution, the pH in the space near one of the electrode was increased and the other one was decreased. The salt solution is what they are saying. At one electrode, pH should increase, at the other electrode, it should decrease during the electrolysis process. For which case it is possible? Let me take first aqueous NaCl, very dilute. See what happens. This is the effect of concentration. When very dilute solution is taken, then the electrode potentials, the respective reduction potential of cathode and oxidation potential of anode values will be actually very low. When compared to these ions, the reduction potential of H2O and oxidation potential of H2O will be more. That means the preferable products for very dilute solution of any electrolyte are due to the reduction of H2O at cathode, that will be hydrogen is liberated like this at cathode, especially for this. At cathode, when water undergoes reduction, 2H2O plus 2 electrons gives rise to H2 plus 2OH minus. This is the reaction that occurs at cathode. That means hydrogen is the product and OH minus is released. OH minus released, that means pH of solution increases. At cathode, at anode, if it is very dilute, instead of chloride undergoing oxidation, water itself undergoes oxidation, or you can say OH minus undergoes oxidation. Anyone can be written. So if H2O undergoes oxidation, H2O gives rise to half O2 plus 2H plus 2 electrons is the reaction. That means during this reaction, if water undergoes or OH minus undergoes oxidation at anode, oxygen gas is the product. Along with this, H plus is released. That means pH of solution will decrease. This happens. When very dilute solution of any electrolyte is taken, these are the possible reactions, and pH at one electrode, pH at cathode increases, pH at cathode anode decreases, but as a whole, there is no more change in the pH because these are neutralized finally. So this is the this is the correct answer for this question, but let us verify the other options also. ZnCl2, when nothing is mentioned, consider that as an aqueous solution of it. The salt solution was, they mentioned, so it is aqueous solution are taken, the aqueous ZnCl2. So what are the preferable reactions at cathode and at anode? So I will give you a hint to decide the product at cathode and anode through this. If aqueous solution is taken, water can compete in reduction reaction at cathode. Whenever alkali metal, alkaline earth metal or aluminum ions are present in the solution, alkali metal, alkaline earth metal or aluminum is present in the solution, then the preferable product will be hydrogen due to reduction of water. If not, if any other metal ion is present, then that metal ion undergoes reduction. That means here it is zinc. So if it is zinc, Zn2 plus can undergo reduction easily. So I will mention that like LK cinema metals, according to electrochemical series, LK cinema metals, what are LK cinema metals? Lithium, potassium, calcium, sodium, magnesium, aluminum. When these metals are present at electrode, then water has more reduction tendency. For any other metals, the reduction tendency is more than water. Now, the product at cathode will be this is case at cathode. So, product at cathode will be due to reduction of Zn2 plus, Zn2 plus undergoes reduction to form zinc. There is no change in pH at this electrode, so this doesn't match with the requirement. Now, at anode, the condition is to decide the product at anode. Here also water can involve in competition with anion to participate in oxidation. If it is chloride, bromide or iodide ions are present, if chloride, bromide or iodide ions present at anode, those ions have more tendency to undergo oxidation when compared with water. If any other ion like sulfate, nitrate, etc. are present, then water can involve in oxidation easily. So, for anodic reaction, Cl minus, Br minus, I minus, they have more tendency to undergo oxidation, next water, next other ions. That means Cl minus can undergo reduction preferentially. So, Cl minus undergoes oxidation to give Cl2 plus 2 electrons. So, no change in pH due to the electrolysis of these ZnCl2. If it is aqueous NaCl, for aqueous NaCl, sodium is present at cathode, that is concentrated. Sodium is present at cathode, that means for sodium, water has more tendency to undergo reduction. So, this reaction occurs at cathode, that means H2 is one of the products at cathode, OH minus is released, pH increases. The other ion is Cl minus. If Cl minus is there, this is the reaction. So, there is chlorine gas liberated, H2 is one product, Cl2 is the other product, but only at cathode there is an increase in pH, at anode no change in pH. So, it is not the option. Copper nitrate, similarly you can decide the product. If it is copper ion, it is not in LK Cinema, it is in the other metals list, positive SRP metal. So, at cathode, copper involves in reduction easily to form Cu. At anode, it is nitrate. When nitrate is present, when other ions are present, water can involve in oxidation easily. So, H2O gives rise to half O2 plus 2H plus 2 electrons. This is the reaction. That means pH decreases. At anode, pH decreases. There is no change in pH at cathode. So, that is also not the correct option. So, the final answer will be first option. Next one. This is the question that was given in cancelled NEET 2026. It is exactly a solved example in NCERT. I have taken it purposefully. It is an example, solved example in NCERT. You can refer the solution also. Let me prove this. Let me solve this with the help of Faraday's first law. A solution of CuSO4 is electrolyzed for 10 minutes with a current of 1.5 amperes. What is the mass of copper deposited? So, mass of copper deposited is equal to equivalent mass of it by 96,500 into I into T. That is, equivalent mass of copper is, its atomic mass is 63 according to the given data in the problem. So, it is 63 by 2. So, that is 31.5. So, 31.5 by that also, actually they mentioned that 96,487 here. This value also they mentioned as exact value is that for Faraday, 1 Faraday is equal to 96,487 into I into T. 31.7, 96,487 into current given is 1.5 amperes, time given is 10 minutes, it should be in seconds. So, 10 into 60 seconds, that will be in grams. This is that 0.2938 grams that you get. Okay. So, this is based on that Faraday's first law. Next question, based on the same point I mentioned, number of equivalents is equal to charge in Faradays. They are asking for how much charge is required. For each of these ions, you can calculate equivalents to get the charge in Faradays. Number of equivalents is charge in Faradays. 1 mole of Al3 plus to Al. The conversion is from plus 3 to 0. That means N factor is 3. That means 1 mole has 3 equivalents. 3 equivalents. For 3 equivalents, you require 3 Faradays. Similar matching was given in NEET 2025. CO2 plus to Cu, 2 equivalents. So 2 Faradays. MnO4 minus to Mn2 plus. Manganese changes its state from plus 7 to plus 2. That means 1 mole has N factor 5. So 5 equivalents. That requires 5 Faradays of charge. That's how to answer that question. So it is 3 equivalents, 3 Faradays, 2 equivalents, 2 Faradays, 5 equivalents, 5 Faradays. Now, this question. A certain current liberated 0.5 grams of hydrogen in 2 hours. How many grams of copper can be liberated by the same current flowing for the same time in copper sulfate solution? That means mass of, when same current is passed through hydrogen and copper, so mass of hydrogen liberated is given, mass of hydrogen by mass of copper, it should be equal to equivalent mass of hydrogen by equivalent mass of copper according to Faraday's second law. So this is 0.5. So we want mass of copper, that is equal to equivalent weight of hydrogen is 1. Equivalent weight of hydrogen is 1 by equivalent weight of copper is 63 by 2, that is actually 63.5. If it is original value is taken, you will get 1 by 30 is 1.75. Oh, no, yeah, they gave 63.5, so 31.75. So mass of copper deposited will be 31.75 into 0.5. That means half of it. That will be this 15.88. Okay, so this is a problem related to Faraday's second law. Let us go with galvanic cells, the most important part. And within that, I am not going to describe the galvanic cell or working of it is not the part of discussion here. I will go with the most important model questions and cover the concept. So first part is electrochemical series. What is electrochemical series? The particular arrangement of different species in the order of their electrode potentials, especially SRP values. So what those values represent? The negative or positive values of SRPs they represent. If a species has negative SRP, it means it has less tendency to undergo reduction when compared with H+. If a species, like for example, K plus is taken, whose reduction potential is minus 2.93 volts. What it represents? It has 2.93 volts less than the tendency to undergo reduction by H+. H+ undergoes more easily when compared with K+, or more easily with any ion which has negative SRP. Positive SRP says that that particle undergoes reduction easily when compared with H+. Okay. So now look at this question that is framed. Reducing power. Actually, based on the same concept, based on the importance or definition of that SRP, SRP is the tendency to undergo reduction. It's the measurement for tendency to undergo reduction. That means oxidizing power of a particle, oxidizing power, that means tendency to oxidize the other, and also it is oxidizing power is the measurement for tendency to oxidize the other, that means tendency to undergo reduction by the same species. This oxidizing power is directly proportional to this tendency, that means it is directly proportional to SRP. Oxidizing power order will be direct order of SRP, whereas reducing power order, reducing power is The measurement for ability of a particle to reduce the other, or the ability of a particle to undergo oxidation. The ability of a particle to undergo oxidation is proportional to SOP, standard oxidation potential, but we have only SRP data. That means it is inversely proportional to SRP. Reducing power is inversely proportional to SRP, oxidizing power is directly proportional to SRP. Based on that, you can decide the order. So, what is the question about? To decide the reducing power order. Which particle has maximum reducing power? The particle with least SRP, the metal with least SRP, metals can act as reducing agents, not the metal ions. Metal ions can act as oxidizing agents, metals can act as reducing agents. So, when you compare different metals, the reducing power order will be inversely proportional to SRP. That means the one with least SRP has highest reducing power, that is K plus minus 2.93 has highest reducing power. Next to that, it is magnesium minus 2.37. Next, chromium minus 0.74. Next, mercury plus 0.79 and 0.80. Silver has least reducing power. As SRP increases, reducing power decreases. Okay, this is the way to answer. For the same question, if they ask to identify the oxidizing power order of different species, to identify the oxidizing power of different species, then that would be reverse. Oxidizing power should be Ag plus with highest SRP. The metal ion with highest SRP has highest oxidizing power. Ag plus greater than, Hg2 plus greater than, Cr3 plus greater than, Mg2 plus greater than, K plus. This would be the oxidizing power order. Okay, based on that powers, like based on this relation, you will be able to identify which is a better oxidizing agent and which is a better reducing agent. Next, it is related to Nernst equation. So, what is the general expression for Nernst equation? For a given cell or half cell, Nernst equation is the relation, mathematical relation to find the effect of concentration on electrode or cell potential. E is equal to E naught cell minus RT by NF ln Q, reaction quotient. That reaction quotient includes both the pressure and concentration terms. It's not like QPQC differently. So, E is equal to E naught minus, the simplified form of it is 0.059 by N log Q. This is the mathematical expression for Nernst equation. You can write it for both half cells and complete cells. Let us solve a question related to complete cell. Let's look at this problem related to hydrogen electrode. Standard hydrogen electrode is assigned 0 reduction potential. Then hydrogen electrode has a different potential. Standard hydrogen electrode should have 1 molar H plus concentration and 1 bar pressure. Under those conditions, it is 0. But if it is any other concentration and any other pressure, that is simply called as hydrogen electrode. For hydrogen electrode, if I take the reduction reaction, 2H plus 2 electrons gives rise to H2. This is the reaction, and corresponding electrode potential can be given as EH plus 2 H2 is equal to E naught H plus 2 H2 minus 0.059 by 2 electrons involved into log of pressure of H2 by concentration of H plus whole square. This is the Nernst equation form for hydrogen electrode. But you can simplify it. When pressure is not mentioned, you can consider it as 1 bar, and this is 0, and finally EH plus 2 H2 can be written as minus 0.059 into log of 1 by H plus whole square. In short, you can write it as minus 0.059 into pH directly. Use it as a short formula. For hydrogen electrode potential, especially reduction potential, H plus to H2 minus 0.059 into pH is the formula. Now answer the question. If it is oxidation potential plus 0.059 into pH, Electrode potential will be more for hydrogen electrode at a pH of. Hydrogen electrode potential will be more if pH is less because there is a negative sign. For lower pH, electrode potential will be more. So that means this C with value 2 is the answer. Let us apply it to a complete cell reaction, Nernst equation for a complete cell reaction. So this is the reaction we have. For this reaction, E cell is equal to E naught cell minus 0. I'll take for convenience 0.06. If it is required, they'll mention it. Because E naught is given only up to 2 digits after decimal, I'm taking it as 0.06 by 2 electrons are involved. Nickel to Ag plus 2 electrons are transferred into log concentration of Ni2 plus by concentration of Ag plus whole square. These are pure solids. Ag and Ni are pure solids. You need not write, or you can take 1 in place of them. E naught cell is 1.05 minus 0.03, this on simplification, into log of concentration of Ni2 plus is 0.160. For convenience, I'll write it as 16 into 10 power minus 2 by Ag plus concentration 2 into 10 power minus 3 square. So when you simplify it, you will get the final answer. Log of 4, 16, 4 and 10 power minus 6, 10 power minus 2, 10 power plus 4. That is 1.05 minus 0.03 into log 4, 0.6 plus log 10 power 4, 4. That means 4.6. So simplify it to get the final answer. Final cell potential under these given concentrations. There is also another application for Nernst equation. It is to find equilibrium constant as well as Gibbs energy change can be related to E naught cell. Delta G naught is equal to minus NF. E naught cell is the expression that can be used to find delta G naught. To get the problem, the cell in which the following reaction occurs is given, E naught is given, calculate standard Gibbs energy and equilibrium constant also. Delta G naught can be calculated with this formula, and E is equal to E naught minus 0.059 by N log Q is the expression, but at equilibrium E is equal to 0, E cell 0, delta G 0, Q becomes KEQ. Therefore, E 0 and Q becomes KEQ. On simplification of this expression, you will get E naught is equal to plus 0.059 by N into log KEQ. Okay, so this is the expression to relate equilibrium constant and E naught cell. Delta G naught calculation. Let us do the delta G naught calculation. It is actually delta G naught equal to the total charge into potential. Electrical work done, maximum electrical work done is equal to Gibbs free energy change, which is equal to charge into potential. That we will get that expression. So delta G naught is equal to minus the number of electrons transferred in this reaction is 2Fe3 plus 2, 2Fe2 plus 2 electrons, or 2I minus 2 I2, 2 electrons. So 2 into 96,500 into E naught cell given 0.236. That will be in the units of joules per mole of reaction it is. Okay, so we simplify this to get the final value in kilojoules per mole. Next, let us calculate equilibrium constant from this. E naught is 0.236. So whenever the simplification part is easy, I am doing it here itself. Otherwise, it will be time taking process. Please try to solve it on your own. 0.236 is equal to 0.059 by 2 electrons transferred into log KEQ. That means log KEQ is equal to 2 into 0.236 by 0.059. This is actually cancelled 4 times and this will be 8. Log KEQ is 8. That means KEQ is equal to 10 power 8. That is the equilibrium constant. For a galvanic cell, working galvanic cell, equilibrium constant values will be bigger because it's a more spontaneous process in the forward direction. maximum extent of completion can be expected. Okay, so you can solve the problem this way. So at last we have another important model of question based on electrochemical series. Let us solve this and close the session. Standard electrode potential for Cu plus to Cu2 plus to Cu is given. That means the corresponding reaction for first case given is Cu2 plus 2 electrons gives rise to Cu. For this E0 is 0.337 volts. Next, second one, Cu2 plus to Cu plus. E0 is 0.153 volts. Now the question is to find E0 for this particular reaction. Cu plus electron gives rise to Cu. What is E0 for this reaction? See, if you have the combination of half cells made up of same metal with different oxidation states, and you observe that you will get this third equation by using these two equations. In which way you can modify these two equations to get third equation? I want Cu on right side, it is there in the first equation, let it be like that. I want Cu plus on left side, it is there in the second equation. Actually, if I take 1 minus 2, I may get 3. Directly taking this equation and making the second equation reverse, I can get the third equation which is required. And if values of E0 are taken, you should not directly take in the same order to get E0 of third equation, because they are intensive properties, they are not additive. But what is additive? The corresponding extensive properties are additive. That means delta G0 corresponding to each of the equation can be taken in this way. That means if you take, you should not take E01 minus E02 as E03. This is blunder. This should not be used. What should be used? Delta G0 values are additive. That means delta G03 is equal to delta G01 minus delta G02. But delta G0 is minus NF E0, that minus NF E0. So for delta G03, I will take it as minus N3 F E03 minus N1 F E01 minus of minus N2 F E02. This is correct process. When two half cells of same metal in different oxidation states is given, and third one asked is also a half cell in the same combination. If it is two half cells given and a complete cell reaction is asked, then you can go for the expression E0 cathode minus E0 anode. But if it is two half cell potentials are given, third half cell potential is asked within the same metal, then the correct procedure is this. Here I can cancel minus F. If it is cancelled, I will get N3 E03 is equal to N1 E01, and here minus NF is cancelled, so I will get again N2 E02. Okay, so this is an expression. If you subtract two equations to get the third equation, use this directly. These N1, N2, N3 are number of electrons involved in each of these steps. First, N3 is 1 electron, E03 is what required, 1 into E03 is equal to, first one, 2 electrons, 2 into E01, 0.337 minus 1 electron involved, so 1 into E02, 0.153. That means this 2 into 0.337. Okay, so that is 0.674 minus 0.153. So try to identify the answer from this. 0.674 minus 0.153, 0.521. So that will be the answer for this question. Okay, so prepare well for the exam and practice the model similar to this. So let us end the session here. Thank you.